Have you ever stopped to think about the vast, completely invisible network operating silently right beneath our feet? I mean, through thousands of miles of steel pipe, literally millions of cubic feet of highly pressurized, extremely volatile gas are surging forward every single minute of the day. Obviously, it's a tremendous source of energy, but managing it? Wow, that is a monumental engineering challenge. How do we safely control that kind of relentless, invisible power? How do we stop it on a dime in an emergency, or precisely route it to light up an entire city or power a massive industrial facility? Well, the answer actually lies in a pretty ingenious and honestly often overlooked mechanical solution. Welcome to This Explainer. Today, we are going to unpack the mechanics of the real unsung heroes of our energy infrastructure, valves in gas transmission and distribution systems. Just to give you an idea of the stakes here, some of these pipelines are operating at pressures well over 1,000 psi. To put that into perspective, that is roughly 30 times the pressure you'd find in your car tires. So we aren't just talking about simple plumbing fixtures here. These are highly engineered checkpoints that make the massive transport of our energy possible, safe, and efficient. Okay, let's dive right into this. Here's a quick look at our journey today. We'll start with part 1, the heart of the pipeline. Then moving to part 2, isolation and quick action valves. Part 3 is precision and specialty flow control. Part 4 covers real-world gas applications. And finally, part 5, engineering safety and impact. Let's kick things off with section 1, the heart of the pipeline, defining the mechanical checkpoints. To truly appreciate the scale of gas transportation, you really have to understand the obstacles we're up against. We're talking about moving fluids under intense pressure across vast distances, which requires absolutely perfect precision to pull off without an incident. So what exactly is a valve in this kind of hardcore industrial context? Basically, it's a mechanical device that controls, regulates, or totally stops fluid flow. Its main jobs are to isolate sections of the pipeline, prevent reverse flow, and protect all that highly sensitive equipment further down the line. Now, when you're dealing with natural gas or specialized industrial fluids, a valve's sealing performance is absolutely crucial. Even the absolute tiniest imperfection can lead to a really dangerous gas leak. The seal literally has to be perfect. And, it's not just about flipping a switch to turn the gas on or off. These valves are performing this complex, nonstop symphony of tasks. They're isolating sections of pipe, precisely regulating the flow, and stopping dangerous reverse flow to make sure the gas only moves in the right direction. They are also the front line for emergency shutdowns, relieving pressure so things don't rupture, and just keeping the whole system perfectly balanced. And because of all this, an engineer can't just pick a valve at random. Getting the right tool for the job always depends on the specific properties of the fluid and the really intense operating conditions it's going to be facing. Moving right along to section 2, isolation and quick action valves. These are our on and off heavy lifters. First up in the toolkit is the ball valve. Now, what's really interesting about this one is just the sheer elegance of its design. Hidden inside the mechanism is a rotating sphere, a ball, that has a hole straight through the middle. When that central opening aligns with the pipe, the gas just flows right on through. But give it a quick 90-degree turn, and the solid side of the ball completely blocks the path. Boom, it's shut. This gives us an incredibly tight shutoff with super quick operation. And since the opening matches the pipe exactly when it's open, you get minimal pressure loss. It's fast, it's efficient, and you'll find them everywhere, especially in compressor stations and emergency systems. Now, contrast that rapid 90-degree action with the gate valve. Think of this mechanism sort of like a massive, heavy-duty drawbridge. It uses a gate-shaped disc that moves strictly up and down. When it opens up, it rises completely out of the flow path. And because that gate is totally out of the way, you get very, very low pressure loss. This makes it absolutely perfect for those giant, high-capacity transmission pipelines, where maintaining your pressure over hundreds of miles is pretty much the whole name of the game. But keep in mind, it's strictly for on-off service. You definitely don't use this one to fine-tune your flow rates. And this brilliantly illustrates the kind of real-world choices engineers are making every single day. We know the gate valve is amazing for large pipelines because it gets completely out of the way. But what if space is super tight? Enter the butterfly valve. Instead of moving up and down, it uses a rotating circular disc right smack in the middle of the flow. It's a much more compact design, it's super lightweight, and it allows for really quick actuation. That makes it the absolute perfect choice for large diameter systems where a giant vertical gate valve just simply wouldn't fit, like, say, the incredibly cramped piping system on an offshore oil platform. All right, let's look at section 3, precision and specialty flow control. Meet the specialized responders. So, We're leaving those simple on-off heavy lifters behind now and entering the domain of the specialists. Because, sometimes the fluid being transported isn't just clean, dry gas. First up in this group is the plug valve. It features a rotating, tapered plug that provides really excellent sealing that makes it the go-to for tough jobs like slurry service or highly acidic fluids. Next, check out the diaphragm valve. This one is fascinating. It uses a flexible rubber diaphragm that pushes downward to stop the flow. The total genius here is that the fluid never actually touches the moving metal parts, so it's incredibly corrosion resistant and super easy to maintain. And finally, we have the globe valve, which relies on a disc moving toward a valve seat. Actually, let's zoom in a bit closer on that globe valve for a second. It's really unique because it allows for very gradual adjustment. Think of it kind of like the highly precise volume dial on a really high-end stereo system. It's not just on or off. It's all about shifting smoothly from a low flow, creeping up to medium flow, right up to high flow. When an industrial process control system needs absolute exact regulation, say they're mixing incredibly precise amounts of gases in a chemical plant, the globe valve is exactly the specialist they call in for the job. Moving to Section 4, Real-World Gas Applications. Let's map out this global infrastructure. So where do all these specialized tools actually live out in the wild? Well, they're spread across a massive, interconnected global network. They're sitting in gas transmission pipelines stretching thousands of miles across entire continents. You'll find them in modern LNG, that's liquefied natural gas facilities, where the gas is supercooled. They're woven through the dizzying arrays of pipes and huge refineries and petrochemical plants, and they're out there on rugged offshore platforms battling the elements at sea. Honestly, every single time you turn on your heat or spark your stove, you are directly relying on one of these valves working flawlessly around the clock to keep our modern world powered up. Which brings us to our final section, Section 5, Engineering Safety and Impact, Defending the System. Okay, so what happens when things go wrong? Let's walk through an actual emergency shutdown process. Imagine a gas leak is suddenly detected in a massive transmission line. Instantly, Step 1 triggers Step 2, automatic valve closure. Devices just like those quick actuating ball valves we talked about leap right into action. That triggers Step 3, full safety system activation, which immediately cascades into Step 4, the emergency shutdown process. Within mere moments, we reach Step 5. The system is completely isolated. The threat is contained. This super rapid automated sequence shows exactly why having the right mechanical checkpoint in the exact right place is quite literally a matter of life and death. So the crucial point here is that the engineering significance of these valves goes way, way beyond basic plumbing. They are the absolute bedrock of system safety and reliability. They're our primary method of leak prevention, making sure that hazardous materials just don't escape. They guarantee efficient flow control to keep industrial processes running without a hitch. And, perhaps most importantly, they are completely essential for environmental protection, constantly working behind the scenes to actively prevent disasters that could totally devastate local ecosystems. Which really brings us to the overarching takeaway for this explainer. Proper valve selection ensures safe operation, reliable performance, and efficient gas transportation. Whether it's a massive gate valve allowing unhindered flow across an entire desert, or a super precise globe valve dialing in a delicate chemical mixture, selecting the exact right tool for the right job is the only thing that guarantees the integrity of our whole global gas distribution system. I want to leave you with this provocative thought. As our energy needs keep growing and our technology continues to advance, how will next-generation engineering continue to optimize this massive, invisible infrastructure operating beneath our feet every single day? The mechanical heroes we explored today, that's just the current state of the art. The future of flow control is absolutely bound to be even smarter, faster, and more resilient. So keep that in mind the next time you turn on your stove or drive past a vast industrial facility humming along. Thanks for joining me on this explainer, and as always, stay curious.